Welcome to Ask and Learn.
Hello and welcome. We are looking at Chapter 5, Section 4, Problem 23. We want to devise a recursive algorithm for computing n squared. So we'll call it procedure square. It's going to take some non-negative integer as a parameter. We want to start with the end in mind, so kind of the bottom of this. A non-negative integer would include 0. So in the case that we reach kind of the end, the bottom, if n equals 0, then we're going to output 0. And we're going to return 0. Otherwise, we need to use this fact they gave us to kind of figure out how we're going to break this down. N plus 1 squared equals n squared plus 2n plus 1. So if this is true, what does it mean for n squared? It means that n squared equals n minus 1 squared plus 2 times n minus 1 plus 1. So if I just, so this is n plus 1 here. So if I subtract n plus 1 by 1, I get to n. And if I subtract all my n's by 1, this is how it shakes out. So else n minus 1 squared plus, and we can at least simplify this last part. We could simplify the whole thing if we wanted to, but this is 2n minus 2 plus 1, so that's 2n minus 1. All right, so this is my procedure. You could work it out a little bit cleaner by multiplying that and combining like terms, but we don't need to, I don't think. Now we want to prove this using induction. So first step, we want to prove that square 0 equals 0 squared. So square 0 equals 0 squared. By definition, I don't think I have to show too much there. That's true. 0 squared is 0. This if statement right here guarantees that square 0 is 0. All right, now for the more interesting step, the inductive step. We want to prove the following statement. If square of n, let's do, I think sometimes it's easier if we do n minus 1. If square of n minus 1 equals n minus 1 squared, then we want to start with that if part and land on this then part. So if square of n minus 1 equals n minus 1 squared, then the square of n is n squared. So we want to start here and end here. So we're going to assume the if, and now we want to look at what's the difference between, I like to look at the more algebraic side, so the right-hand side here and the right-hand side there. And if I kind of do the same thing to both sides of an equation, that usually ends me where I want to be. So n minus 1 squared is n squared minus 2n plus 1. So I have my n squared here. The problem that makes it different than this is minus 2n plus 1. So if I add 2n and subtract 1 from this here, both sides of the equation, of course, then I'm going to be left with n squared. So that's what I'm going to do. So I could say, then clearly, I'll write it down here so I don't run out of space. The square of n minus 1. So this equals n squared minus 2n plus 1. So I'm going to add the 2n over here and subtract the 1 over here. That leaves n squared here. So I got n squared here, which means that this over here, if what I'm proving is true, should really be square n. And so to prove that, I'm going to look at what is square n. We know square n equals, and then I want to use the procedure to find what square n equals. It equals, well, I guess maybe I shouldn't have been lazy before. I should have multiplied it out. Equals n minus 1 squared plus 2n minus 1. Let's see. So, oh, here it is. So at the beginning, we assumed that square of n minus 1 equals n minus 1 squared. So we can keep using that fact. So we can say then square n equals, so this right here is the same as this right here by this statement here that we're taking for granted, equals square n minus 1 plus 2n minus 1 as wanted. And then maybe I should add also equals n squared from this equality here. So that is the end of the proof.